Alright, so welcome back. So in today's meeting, we will be covering the universe's structure as well as the multiverse theory. We will see all the different divisions that astronomers have named in the universe, and we shall also see what the multiverse theory really states. The next slide, please. Alright, just before we start, here's a quote by Einstein. It is not the result of scientific research that ennobles humans and enriches their nature, but the struggle to understand while performing creative and open-minded intellectual work. Alright, with that quote done, let's dive in. Alright, to start off, we need to understand what the fundamental particles are, so we have quarks, and these quarks are basically the fundamental particles that make up the universe. There are two states that quarks can be in. The first state is up, and the second state is down. So you've got up quark and down quark. Now the combination of three quarks makes the protons and the neutrons. The electron, like the quark, is another fundamental particle. From the protons, neutrons, electrons, atoms are made. The protons and neutrons are centered within the nucleus, and the electrons orbit it. Even though we usually see models of atoms with the nucleus having a relatively big size compared to the atom, in reality, the size of a nucleus is very small compared to an atom. If a nucleus is the size of a needle, the atom would be the size of a football field. That's American particle. Atoms make up molecules, which makes up bigger things in the world, starting from dust, things like the sun. And now we move on to the Earth. Now the Earth, for those who don't know, is the planet we live in, and it's made up of plenty of atoms. It is currently the only planet that has been confirmed to have life. It is the third planet from the solar system, which means that it is in the Goldilocks zone, which is basically the zone where everything is just right. The temperature is not too hot, and it's not too cold, it's just right, so hence the Goldilocks. Now the Earth's axis of rotation is tilted by about 23.7 degrees, and this causes seasons. Moreover, the Earth also wobbles, and this wobble occurs once every 70,000 years. And as we zoom out, we come to our solar system. Now, of course, this solar system is just to show the planets. It's not, the planets aren't all in this straight line. So anyway, so this is our solar system, and our solar system consists of 8 major planets, of which 4 of them are rocky planets, the small ones to your left, and 4 of them are gaseous planets, which include Jupiter, Saturn, Uranus, and Neptune. Now, the term rocky planets refers to those planets that are primarily made up of silicate rock or metals, while gaseous planets are made up of gas. If you were to try and stand on a gaseous planet like Jupiter, for example, you would fall right through because there is no solid surface. It's all gas. The gaseous planets are known for their sheer size as well as their numerous moons. And fun fact, if, for example, if you took Jupiter and you added a bit more mass, it would have potential to become a brown dwarf, which is a type of failed star. So in essence, Jupiter and the Sun are made up of the same thing. Now, before we go ahead, we must get accustomed to certain relative units. This is due to the sheer distances and extremes in space. For distances, we consider 2 units. We have the astronomical units and light years. Now, the astronomical units, or AU, is the average distance between the Earth and the Sun. We use the AU primarily when dealing with celestial bodies within our solar system. For larger distances, we use the light year. Be informed, the light year is not a unit of time. Rather, it is a distance that light travels in a span of 1 year. It's equivalent to 9.5 trillion kilometers, which is about 13.5 billion trips to Chiang Mai from Bangkok. For temperature, we use the Kelvin scale. and Kelvin is based on thermal energy. This means that at 0 Kelvin, at 0 Kelvin, this is the temperature where all matter stops due to lack of energy. We also use very large numbers such as quintillion, quadrillion, million, billion, trillion, and so on. Now in our solar system, there are a bunch of regions. Now two regions, or one particular region that is very important to us is the heliosphere. And it's this yellowish region here. Of course, there's no color like that in space, but it's just to, identify it. But what is a heliosphere? Well, the heliosphere is this region that surrounds the sun. And it's basically this place where the sun's solar magnetic field and the protons and electrons from the solar wind reach. Now, why is this important? Well, this region means that we're protected from interstellar radiation from the rest of space. So anything within this region is protected from interstellar radiation. And now we get into the structure of the solar system. The solar system consists of an asteroid belt between Jupiter and the Earth, which you can see over here. And this is situated about 2.2 to 3.2 AUs. And some astronomers even believe that due to the gravitational field of big planets like Jupiter and Saturn, the Earth is actually protected from destructive comets and asteroids. Moreover, after the orbit of Neptune, the last planet in our solar system, we have this thing called the Kipper Belt, which is situated around 30 to 50 AUs. Now the Kipper Belt is home to dwarf planets like Pluto. Currently, there are 6 recognized dwarf planets: Pluto, Ceres, Eris, Makemake, Haumea, and 2015 RR245. Please excuse my pronunciation. Although there are 6 recognized dwarf planets, astronomers nowadays have looked into the Kipper Belt, and they found around 20 more similarly sized celestial bodies. As we zoom out further, we have this Oort cloud. And now the Oort cloud basically engulfs the whole solar system. The Oort cloud is said to be the home of the comets, which are these icy objects with dust. And this is situated around 2,000 to 100,000 AUs. Next slide. The latest comet appearance, or the most famous in recent times, was Comet Neowise. And I believe this came in 2020. Unfortunately, I wasn't able to spot it. As we expand further, we also see that the planets and all celestial bodies aren't the only thing that are in an orbit. The Sun, and hence the whole solar system, follows an orbital path around the center of our Milky Way. The Sun basically acts like a tugboat, dragging everything with it. And as we zoom out further, we see a path in the Milky Way. We are moving at an average velocity of around 828,000 kilometers per hour. But even at that high rate, it still takes us 230 million years to make one complete orbit around the Milky Way. I'll repeat that. It still takes us 230 million years to make one complete orbit around the Milky Way. And to make matters even more interesting, in the center of our galaxy, the Milky Way, most astronomers suggest that there is this supermassive black hole. Now, a supermassive black hole is just this type of black hole, but supermassive, right? And it's in the center. Now, just know this, we'll cover black holes in detail in another meeting, but black holes are these massive, amazing objects in space where the gravitational field is just super strong that even light can't escape. It's just this monster that eats into anything that comes into its field, right? And as we zoom out further, our Milky Way isn't the biggest thing. Now, what we have here is called a local group, Now, the local group is basically a group of 30 galaxies, and the most prominent of these galaxies are the Milky Way and Messier 31, also known as M31 or Andromeda. And others include the Triangulum Galaxy, M33, Leo 1, and NGC 682. Now, the local group has a diameter of around 10 million light years, and the next slide will show you the relative distances from other galaxies to our galaxy. As you can see here, up to the left corner is Andromeda, and astronomers believe that in a certain amount of time, Andromeda and the Milky Way will collide into each other to create one supermassive Milky Way. But that's not going to be tomorrow or next year. It's going to be for a very long time in the future. Next slide, please. And as we expand even further, the local group actually lies on the very edge of this bigger group called the Local Supercluster. And this Local Supercluster is in the very center of the Virgo galaxy cluster. Now, the local group seems to be revolving around the center of the Local Supercluster at around 400 kilometers per second. Now, the Local Supercluster, or the Virgo Supercluster, shares a spot in the sky with the constellation Virgo, hence the name. This means that you can actually spot this with a powerful enough telescope, and we will get into telescopes in the near future. But now scientists aren't quite sure of why it is in this specific spot, in the spot of Virgo. It could be by chance, but what we do know is that the Virgo galaxies seem to be moving away from each other at a constant speed, and are hence dynamically related. Moreover, the local supercluster is around 100 million light years in diameter, so extremely large, and it has a collective mass of around 10 to the power 15 solar masses. In other words, it's 10 to the power 15 times more massive or more heavier than our sun. As we move on further, I have a lot of trouble pronouncing this, so I'm going to leave the pronunciation to the end. But this structure is basically the distribution of mass and the relative velocities of the galaxy clusters. Now I'll explain what that means. If we plot the mass and the velocity, as well as the direction that the various galaxy clusters take, then we can form this sort of pattern. And as you can see, this pattern is it looks like strings, right? Now, all these strings basically show the direction and the velocity and the relative mass distribution of the galaxy clusters. Now, this pattern is called Laniakea. Yeah, I hate pronunciation. I can't pronounce it. Alright, so in Laniakea, there are galaxy clusters that move towards us, the Milky Way over here, and others that move away from us. As mentioned, we are part of the Virgo cluster of galaxies, right? And this cluster, as well as many others, seems to be moving towards a particular region in Laniakea. And this region is called the Great Attractor. There's a lot of debate about this topic, and some say it's bonkers, but no one is for sure. And this gives a better graphical representation of Laniakea with the mass and the relative velocities. Finally, we reach this thing called the observable universe. Now, the observable universe is what humanity will ever know and has ever known. Now, the observable universe is about 46.5 billion light years in diameter, whereas the non-observable universe, which is outside this circle, is about 23 trillion light years in diameter. Now, you may be wondering why it's named non-observable and observable. Well, simple answer: the non-observable you can't see, the observable you can actually see, hence the name. Now, the sad reality of space-time is that as space expands, so does every spot. Now, I'll demonstrate this fact in a simple animation that we've created. The next slide. Now, in the first scenario, let's say that we are here on Earth, right? And this orange dot is some galaxy, some distant galaxy. The catch is here. That galaxy is within our observable universe. So when that happens, this arrow signifies a light ray. And the only way we can observe things is if the light from that particular object, in this case that galaxy, reaches the Earth. This trapezoid demonstrates the space between the Earth and that galaxy. Now we'll go ahead and play this. As time moves on, that space between the Earth and that galaxy expands. However, since this is in the observable universe, this means that the light from that galaxy to the Earth actually has enough time to reach the Earth. Now, if we go on to the next scenario, this object is in the non-observable, that same orange object now is in the non-observable universe. Now, what happens here is, if you play the animation, the distance is so vast that the light ray simply hasn't got enough time to reach Earth. So in other words, anything in the non-observable universe will forever be non-observable. And with this, we finish off with the multiverse theory, and Gideon will cover this.
So the term multiverse was first coined by an American philosopher named William James in 1865. Used it to refer to the confusing moral meaning of natural phenomena, not to mean the possibility of other universes existing like we use it to mean today. The multiverse is a hypothetical group of multiple universes. Together, these universes comprise everything that exists, the entirety of space, time, matter, energy, information, and the physical laws and constants that describe them. Different universes within the multiverse are usually referred to as parallel universes or alternate universes. A lot of scientists include it and take it seriously. However, we cannot observe these alternate universes. It is not based on observational data.
Thank you, Gideon. And with that, it brings an end to today's meeting. We hope you enjoyed what we presented.